So this D dash is representing a thermodynamically corrected diffusivity, which kind of well, they kind of go, they're like, it's more, I guess this is better. Definitely correlated to 1 over frictional coefficient. And this is, frictional coefficient is coming from the hydrodynamic interpretation of the diffusivity. Because it makes sense, the less friction, so less drag we have, the faster it will diffuse and higher diffusivity, right? And this is true for when this infinitely diluted diffusivity is the same as the thermodynamically corrected version. But in real life, there's no infinitely dilute. So going from like ideal situation into like the non-ideal / the real life example situation. So we have the diffusivity in like Vignes correlation, where this kind of works, where there's infinitely dilute diffusivity of ij and ji with the exponent of xi, the concentration of I and concentration of j, concentration of I, and we get this infinitely diluted version or diffusivity through the Wilk and Chang equation. And once we have that, through that we can get the Vignes, and we can get like the actual non-ideal or practical diffusivity by multiplying it with the Vignes with the thermodynamically non-ideal correctional component, which is RT. T is temperature, R is the Boltzmann constant, or no, what is it, R? No, the R is gas constant, which is just Boltzmann constant times the Avogadro's number constant, and then 1 plus xi, the component, the concentration of I, and then D ln gamma, which is the activity coefficient when it's so it represents how ideal the solution is, and when it is ideal, it goes to 1, and ln1 is 0, and then this becomes 0, and then it's just the whole all of these become like 1 because this is 0 anyway, and then dxi, which is the concentration. So we can definitely tell this is concentration dependent. The diffusivity is concentration grade dependent. So for example, we have this ethanol and water mixture, and this is like the infinitely diluted diffusivity of ethanol and water. So ethanol water and water in ethanol mix. And like in the table, we kind of looks like this, where this represents concentration of ethanol, so it goes from 0 to 1, and then activity coefficient goes from, I guess, 1.95 to 1. It is kind of questionable why this is like 2 instead of 1, where this is pretty much just water. But I guess it makes sense in the fact that the activity coefficient is representing ethanol, not water, so it's as far away from the ideality as possible. So we have this high, much higher than 1. And anyway, and this one is representing the thermodynamic non-ideality over here in this column, and that they tend to have this like a U shape. So it's low minimum over here in the middle, and then we have this diffusivity EW, and it got 1.28 and 1.13, but in between. So that's infinitely dilute on each side, but in the end it kind of like dips in. So if you put it in a graph like this, that's kind of how it looks like. It's not really to the scale, but that's what it should look like, where this is the concentration of ethanol. So that's from experimental result. So that's kind of depends on the concentration and how it works, I guess. But it's good to ask like why. So what's the interpretation? I'll ask that and put it in the description later. So diffusion of gases and small molecules in polymers or other solids. So di, the diffusivity of I, is di times e to the power of the negative e ti over rt. I'm gonna come back to this, and I don't. But in the when we like put it experimentally, this is 1 over temperature, and then like diffusivity in log. Like different solids have, and polymers like shows there's 2 distinct lines, and the one is glassy type of solid and one is rubber type. I guess this is when I start to get solid and it doesn't really make sense, but I'll continue. Extension to multi-component system. So this is Maxwell-Stofan approach. At the beginning, I talked about the D dash, the thermodynamically corrected diffusivity, and that's what this is really representing. And so what is happening in our like actual diffusion process is that we have different molecules, and this one molecule goes to like pretty fast speed, and the one next to it that's kind of different and going at different speed. They have this molecular interaction that's kind of pulling each other. So even this molecule A is kind of like tagging on molecule B too. So they kind of that's what really Maxwell-Stofan approach is really trying to explain, represented with this equation. And there we see this D dash again, the thermodynamically corrected diffusion coefficient. And we call this here Maxwell-Stofan diffusion coefficient. And to make sure this is not a Fickham diffusion coefficient. And this is just the flux with TEA. TES is a triethylamine T's. And then this is Gibbs free energy over just the Z, the axis coordinates. Yeah, so it's just trying to show that it fits the Fick's law, first law. So near the phase boundary of mixture between the triethylamine and the water, what we see here is that, so this is the concentration of TEA and the x-axis, and diffusion coefficient on the y-axis. And we see this dip going there where the diffusivity becomes negative. And you know, that doesn't really make sense. So if we convert it into, instead of concentration, because we know that what really drives the diffusion process from like high concentration to low concentration, it's not really the concentration gradient, it's really the chemical potential gradient. So if you convert the x-axis into chemical potential gradient, we see that there's no negative diffusion coefficient, which makes a lot more sense than negative diffusion coefficient. And so it's a good news that it's not a negative, there's no negative diffusion coefficient. And if we show the Maxwell-Stofan diffusion coefficient, it will kind of goes like that. And then, so imagine we have this like two containers, and there's a valve in between, and then the A has a mole fraction of helium 0.5 and nitrogen 0.5 and CO2 no CO2. There's a no helium, and we have the same number of nitrogen and the same amount of nitrogen and 0.5 mole fraction of CO2. Okay. Or 50% CO2. So we can imagine when we turn the valve on or open the valve, what happen is that helium will go to 0.25 on both of them, CO2 to 0.25 for both of them, and nitrogen will just stay 50% for both of them. However, that's not really what happens in reality. As the time, this is time axis, and then this is like the concentration or mole fraction. So helium and CO2 really in steady state approach it to 25%, but with the nitrogen gas at the beginning it kind of increases and then approaches 0.5. So what's happening over here? Because and that's because of the Maxwell-Stofan couplings that we talked about here, how the one movement and the molecules kind of tag along, kind of influences other molecules' movement by kind of like dragging along the other molecules through the intermolecular interaction. But we're still going uphill in terms of energy / chemical potential. So what's happening? So if you look at the total free energy of the system, so not just nitrogen but of helium and CO2 as well, the total free energy is continuing to decreasing. And how this is happening is because the asymmetrical molecular interaction of different molecules. So the strength of the molecule interactions are different between helium and nitrogen, nitrogen and CO2, and CO2 and like helium. And because of that, it allows this weird phenomenon to occur. So this likely goes back to the frame of reference effect. So imagine we have this like fluid flow. The fluid is made of this different type of molecule A and B, or chemical B A and B, and we're going through this tube, and we have this plane 1. And on here somehow there's a high chemical potential energy of A, and then here on the downside that we have this low chemical potential A. And so we can definitely suspect that it has to be true that there is some sort of a movement of this diffusion of A because of the differences. So first there's total motional flux of A through this plane 1. One component is the convection, the fluid flow of A through 1, because that's what's happening, but also the diffusion of A for a molar average frame of references. And I will further explain this molar average frame of references later.